So our project is on the harmonic content in photovoltaic generation farms, and my name is Francisco Martinez.
I'm Mike Isley.
I'm Monique Sains.
And I am Serafino. All right, a brief introduction. High demand of renewable energy has allowed renewable energy to be the fastest growing energy source. As of today, renewable energy has made up more than 17% of the United States power generation. Out of this 17%, 11% is contributed by the solar generation or photovoltaic power generation, PV. PV power generation is expected to grow by 48% by 2050. An increase of production contributes to large generating farms, thus increasing the amount of harmonic injected into the system. Harmonics contribute to the power quality, creates problems. Our research is pretty much is concentrated in harmonic controls with the power system, within the power system, particularly the effects created within a PV system. PV systems have shown harmonic distortion generated by the PV inverters. Harmonics are current and voltage multiples of the fundamental power frequency. Harmonics affect the power quality of a system. These problems can result in distortion within the voltage source, loss in transmission and distribution, preliminary failures within the equipment, and overheating in transformers. Within PV power generation, harmonics control is crucial as the level of power transformers is drastically impacted. High order harmonics create higher losses, early fatigue of insulation, and premature failure.
So these are the equations that we use to prove that higher order harmonics are generating heat in the transformers and reducing the life. So the equation here, PE equals KE PM squared times the thickness of the lamination meters squared times the frequency of reversal of magnetic field in hertz squared times the volume is the PE equation. It's the equation for eddy current losses in transformer at fundamental frequency. So basically we take that equation and we plug it into this one to get PEH. We plugged in PEF, and now we're gonna plug in the sum of the harmonics squared times the current at those harmonics squared. So these eddy current losses can be associated with a temperature rise in the transformer windings. Using this equation here, heat energy equals mass times the specific heat capacity times the temperature rise. And we can associate that with that last equation, PEH times time. We'll manipulate this equation to get the temperature rise, which is PEH times time over mass times the specific heat capacity. So the standard, the IEEE standard states that an average winding rise of 65 degrees Celsius shall not be exceeded when the transformer is operated at its rated load. We can use this regulation to prove that if the higher order harmonics cause eddy currents to build up in the transformer windings and produce heat, the life of the transformer will be significantly reduced due to a breakdown of the winding installation.
Equipment. So the first piece of equipment was the M871. This meter was utilized to record and measure data. It's capable of measuring THD, TDD, RMS volts and amps, individual harmonics, and more. It's ideal for monitoring and recording an AC distribution and transmission systems. It features one set of a three-phase current inputs, two sets of three-phase voltage inputs, two waveform recorders, and various configurations. The next piece of equipment is the M571, and it was also used to collect data. It can take single phase to three-phase measurements of current and voltage.
For graphics and calculations, the K value, with the help of the MATLAB, we can calculate a K value from the given data for a day of recording. Our K value was an average of all the values throughout the day, and it came out to be 338.9646. And the harmonics, we captured all the way up to the 64th harmonic order. And the software was Wavewind by Bitronics, provides a breakdown of the readings collected from the M871 power quality meter. Files contain the current, voltage, THD, and the harmonic readings up to the 64th harmonic. The 70 series configurator allows the user to set up a connection between the meter and an external device such as a laptop, where data and settings can be transferred and configured, and MATLAB provides fast calculations for complex equations.
Conclusion. The goal of our research was to prove the presence of harmonics and then provide and test a few helpful mitigation techniques that would extend the lifespan of transformers, such as an isolation transformer. Adding insulation and separation of windings prevents damaging eddy currents that occur due to higher order harmonics. Also, solar tracking device. Fitting solar panels with trackers allows for optimal sun angles, reducing voltage fluctuations, in turn reducing harmonics. The M871 would be implemented to gather harmonics data at a location implementing an isolation transformer and a separate location implementing solar trackers. This will be used to compare to a location that does not have either to test which mitigation technique is more beneficial. The two factors to consider are which option is the most economically viable and which option provides optimal energy production.